Ooh, hey, we are going to be ramping up the physics today. This dude is just that plain black cylinder I had used before. I put the smiley face on there because he's adorable. But I did that so you could tell that if he is on this incline, this is him sliding or slipping, is what they call that, slipping. If he is then rotating, then you can tell by the face being rotated that he is in fact going in circles, because just a plain black cylinder, it's hard to tell if he's rolling or sliding. Okay, what I want you to also be able to visualize is the friction that the board, the ramp, is applying to this cylinder. If I just place him on the cylinder and just let him go, all right, friction is grabbing onto him in this location, trying to prevent him from going downhill. So if we're trying to prevent him from going downhill, friction must be pulling him uphill. All right, cool. That's true if he's sliding. And it's also true if he's in fact rotating, because if this board were frictionless and I set him like here, he would end up sliding down here and he would go downhill without rotating, and it would play with your head a little bit. So please remember, if you're going downhill, whether you're sliding or rolling, friction is acting uphill, okay? And what we will do a little bit later on is we'll find out if that is true even if you're going uphill. Okay, so what we're going to do, torque part D, rolling without slipping, okay? So that's the cylinder with a radius and a mass. The distance that the hill is just a delta x, all right? The angle is theta, the height is h. So we're going to start doing more math with just letters now, okay? Math with letters. So we got a solid cylinder. Its initial velocity is 0 at the top. It'll roll without slipping. It wants to know what the speed of this guy is at the bottom of the hill. But use letters, all right? H's, R's, M's, and when it says fundamental constants, that means you can use little g, all right? Little g. So what we're going to do is we're going to identify the forces that are acting on that cylinder, which I was trying to show you down there. But this dude, then, there's gravity. You guys know gravity listens to my favorite band, which is One Direction, straight down. There's FG, all right? You guys are used to breaking gravity into this perpendicular component, that parallel component. That red arrow is FG parallel. It is sine theta. You know that by now, right? So that's the component making this guy want to slide downhill. Now, what did I say friction does? Friction then acts at the spot where this wheel is in contact with this surface, which is, I'm going to make this a little thicker with a green arrow, and I'm going to say that so you can see it a little easier. It's acting on the surface of the hill, uphill. All right? So those are the arrows. So there, it's the sum of the forces parallel equals ma. That's the acceleration of the center mass, the acceleration of this guy, linear acceleration. So the force gravity parallel, mg sine, I should use the correct color, but anyway, it is mg sine theta minus the force of friction equals ma. All right, now, many of you would wish to call that force of friction mu Fn, and I don't blame you for wanting to Fn do that, but please do not Fn do that, because that, again, mu Fn, it is only true if it's sliding down the hill, but this is rolling down the hill now. So please do not call that force of friction mu Fn, all right? Do not Fn do that. So what we're going to do is add up torques now to get what that Fn, or I'm sorry, what that FR, what that force of friction is. There are torques around the center mass. If this guy is going downhill, the first thing I'm going to do is pick an axis of rotation. It will be that purple triangle. That's the axis that it's going to rotate around. All right, so there are two torques acting on this guy. There is the torque due to gravity, and there is the torque due to friction. Those are the only two torques acting on him. The torque due to friction, the torque due to gravity. Okay, that's it. So if those are the two torques acting on him, gravity is making him want to rotate this way. Friction is also making him want to rotate that way. So they're both acting in the same torsion. But what I also want you to realize is how far away is that gravity arrow from the axis? Very good, none. It's 0 distance away. So this will be a torque due to gravity plus the torque due to friction is now the I. Remember that I, 1/2 mr squared, okay? It's a solid cylinder, so 1/2 mr squared times alpha. So the torque due to gravity is 0 because the R of gravity is 0. All right, so the torque due to friction now is the force of friction times the radius. It equals 1/2 mr squared alpha. Now, the next thing I'm going to do is I am going to rewrite this 1/2 mr squared alpha. I am going to rewrite it as 1/2 mr alpha. Okay, so that R alpha is what I should have written over there. I had that in the wrongs. This R alpha, eh? That should sound familiar. So that R alpha is the linear acceleration. Ralpha is A is ralpha. So what I can replace all of this with is the torque due to friction is 1/2 mRA. And whoops, the torque due to here. Let me rewrite that there. The force of friction times radius. That's what I will write. So this force of friction times the radius. The force of friction times the radius is 1/2 mRA. Now I can kill the R's, and I can now say the force of friction is 1/2 MA. All right, that's what I can now say is the force of friction. So as I'm putting numbers in this equation up there, the force of friction now is 1/2 MA. Okay, so I'm going to put that where force of friction is. I'm going to rewrite that into the sum of the forces equals MA equation above, which I just showed you. The mg sine theta minus the force of friction is MA. All right, mg sine theta stays the same. Remember that force of friction? We just said it's 1/2 MA. It's right there. So I'm going to then move it over by pushing the plus button. This becomes, gosh dog it, let me get back to a black ink. This becomes mg sine theta equals, now this is an MA plus a 1/2 MA. That's 3/2 of an MA. So if I wish to solve for what that A is, what I am going to say is going to multiply it by 2/3. Ooh, gosh, we even get to go to history class, can't we? Oh, we can kill the masses. So the acceleration of that item is 2/3 g sine theta. All right, that's the acceleration of this item as it's going downhill. Remember, it's an acceleration, so it doesn't matter what the mass is. It just matters what planet you're on and how steep the angle is. All right, and then this friction or this fraction, sorry, that fraction is determined by what shape this guy is. Okay, so now what I'm going to do to answer the question, how fast is it going at the bottom of the hill? I'm going to plug that A into the 5-ULA formula. All right, so we don't know time. All right, and we already said the initial velocity is 0. 2 is 2. Now what did I get for A? A, I just said, is 2/3 g sine theta. Now, what is that delta x? That's the distance it rolls. So along the incline. All right, that's basically the hypotenuse. That's the length of that piece of wood there. So that delta x is h sine theta, okay? This distance, delta x, is h times the sine of theta. So that's the other Swapartuna delta x, all right? So what I will do is put all of that together. The VF squared, that VI died, it's 2 times 2/3 g sine theta. That's what A is, and the delta x is h sine theta. So what I finally end up with is all of that kill what needs killing. The sine thetas die, and it's 4/3, 4/3, and that is g times the h, and I'm going to square root that. So the final velocity at the bottom of that hill in terms of nothing but m's, g's, h's, delta x's, whatever, all of that is just 4/3 gh square rootified. That pattern I want you to remember, okay? The only thing that would change is if it were a hollow cylinder, if it were a solid sphere, a hollow sphere, whatever, anything rolling downhill, it will be some fraction in front of GH square rootиfied. That will always be the true. If it's any different shape, the only thing that would change is the fraction inside that particular square root. Okay, so now what we're going to do is take a look at the force diagram again, and what I want you to be able to ascertain is if you look at just the force diagram, are we rolling uphill or are we rolling downhill, okay? So what I'm going to do is tell you, in this case, we're rolling downhill. I'm going to once again draw gravity, all right? I'm going to draw the perpendicular component. I'm going to draw the parallel component. That, again, is what we're referencing. This green arrow right there is where friction is. That's something that we already said we could identify from our last drawing, right? If you're rolling downhill. So again, it's what the surface is doing. It's grabbing onto this, trying to prevent it from sliding downhill. So the torque that gravity applies is that multiplied by that small little distance there, if we which I'll show you another way to get the torque if you put the axis of rotation right there. Okay, we'll probably get to that in a different video. So it tries to prevent it from sliding downhill. Therefore, friction must try to grab it and pull it uphill. Okay, now I'm going to draw the exact same incline and say, what if it's rolling uphill now? What if this item that I showed you a little bit ago is rolling uphill? Okay, and in order to get it to roll uphill, what I need you to realize is if this thing's going to roll uphill, and here, let me move it over again to get you to see the incline. Okay, now, if this thing's, if I just set it on here and let it go, you know it's going to go downhill. It's just that gravity pulls things downhill, kids. So if this item is going to go uphill, there needs to be some external force making this wheel rotate like the engine of a car. Or it needs to already be moving, like rolling, by the time it gets to the bottom of the hill, and then it's going to keep rolling uphill to some certain height, right? So if you're rolling uphill, there has to be some motion already where the wheel is pushing backwards on that contact point. And the road, the board itself is trying to prevent it from slipping instead of doing one of these, all right? So if it's trying to prevent this portion of the wheel from going that way, it must be grabbing onto it and pulling it that way, okay? So it's a very odd thing, but if we're already moving, just remember that if you're going to go uphill, there needs to either be an external force or it needs to already be moving in order to move uphill. So that then means this diagram. This diagram is going to be exactly the same. There's gravity, there's perpendicular, there's parallel, and again, friction is still acting along the incline upwards. So it's trying to prevent slipping at the contact point, or think of it as the third law, where if the wheel is pushing back, or down the incline must be pushing up, okay? And if it's rolling on level ground, you guys all know that, then the wheel is pushing that way, friction is pushing that way, okay? So please be able to visualize torques and inclines, and that is a kinematics version of torque making you roll downhill. A joke I say is leave it to a physics class to take something as simple as rolling downhill and turn it into all that math. Ooh, that's a lot, but that's some good stuff. So that is a kinematics version. When you use 5 EULA, remember that's a kinematics way to get the velocity at the bottom of the hill. I will show you a little later on an energy way to get the velocity at the bottom of the hill. But I have one more video to do that next, which will be torque around pulleys. Anyway, coming up on 15. Yay, physics!